This program is being presented to you by the WE-Heraeus International Winter School on Gravity and Light.
Hello and welcome back to the 5th tutorial of the WE-Heraeus International Winter School on Gravity and Light. Today about tangent spaces. Again, we will start with a few true or false questions to spark discussions in the tutorials and here for you as a self-test. So we have to tick the correct statements but not the incorrect ones. A. A tangent vector to a differentiable manifold has a length and a direction. Well, while you could argue that the direction is given by the tangent vector as a new kind of terminology, it certainly has no length in a general setting. Because, as you will see in one of the following lectures, a length is only defined when you have a metric on your manifold, and in general you have not, so the first option is wrong. A tangent vector to a differentiable manifold must not be zero. Well, let's have a look at the definition of a tangent vector. The tangent vector v was defined by a curve gamma at a point P by its action on a function f on the manifold. And how does it act? Well, you have to compose the function with the respective curve, take the derivative of it, and evaluate at the point lambda naught. What is lambda naught? Well, it is the parameter value where the curve gamma takes the value p. So gamma of lambda naught is p. Now, if we have a curve gamma which remains stationary at the point p, so imagine you have your manifold M, here your point p, and your curve gamma does something, and at the point P it stays there for a time and then carries on. This derivative will be zero, of course. And the tangent vector would be the zero map from C infinity M to R. So yeah, it can be zero. So this second option is wrong as well. A tangent vector to a differentiable manifold maps a function on the manifold to the real numbers. Well, I just gave you the definition of a tangent vector. Here you take a function on the manifold, and here you get a real number. So a tangent vector is mapping a function on the manifold to the real numbers. So this is correct and we can tick it. A tangent vector to a differentiable manifold is of the same dimension as the manifold. What is the dimension of a vector? The answer is we didn't define dimensions of vectors. A vector is only a vector in the context of a whole vector space, and this vector space may carry a dimension, but not the vector itself. So this option is wrong as well. A tangent vector to a differentiable manifold arises as the velocity to some curve through the vector space point. Yes, this is true. We defined these velocities, showed that they constitute a vector space, and any element of this vector space we call a tangent vector. So by its very definition, this option is right. Question B. The tangent space TPM to a d-dimensional differentiable manifold is of the dimension 2 times dimension of M? Well, no, this is to delude you. We will see the dimension is only 1 times dim M. 2 times dim M would be the dimension of the tangent bundle, to which we will come later. So this option is wrong. The tangent space can be defined at every point P of M. Yeah, why not? Let's again take a look at the definition of the tangent space TPM. The tangent space TPM is just defined as the collection of all velocities of curves through this point P. Yeah, where gamma is just a curve through this point P. And here we didn't make any restriction on the point P, so it is valid for every point P. There's no sense, no real reason to restrict it. So this option is right. The tangent space TPM is no real vector space because its elements are only tangent vectors. This is of course wrong, because in the lectures you showed that you can equip this tangent space with an addition and scalar multiplication, and you showed that the axioms for a vector space hold, so of course it is a vector space, and these elements are called tangent vectors because we call this vector space the tangent space, but nevertheless it is a vector space. The tangent space TPM to a d-dimensional differentiable manifold admits a linear bijection to the vector space Rd plus circ, where plus shall be the component-wise addition on tuples of real numbers, and circ the component-wise multiplication with a scalar. This is of course true, because in the lectures you checked that TPM to a d-dimensional differentiable manifold in fact is a d-dimensional real vector space. And it is a fact that every finite dimensional vector space with dimension d to the real numbers is isomorphic to the vector space Rd, which is written here. And the linear bijection between vector spaces is just a vector space isomorphism. So this is true. The tangent space TPM has no tangent vectors in common with the tangent space TQM for a different point Q, which is not M and not P. This is right, as you can see on the definition of your tangent space. It is defined via these objects, which are defined by collections of curves through P, the point P. And of course this collection looks different at any point P. So true. Question C. If Ux is a chart for a d-dimensional differentiable manifold, then the coordinate maps x, y mapping from the chart domain U to the real numbers R, with I running from 1 to the dimension of the manifold, are only continuous, not differentiable. Well, first, it is true that the coordinate maps are defined as being continuous maps into the real numbers with continuous inverse. So pictorially, we have the chart domain U and coordinate maps map into the real numbers. This is the coordinate map xy. And here on this level you can only check for continuity, because here you have no structure to talk about differentiation. But now we can look at what happens in a chart. And here we may take the same chart X, which is very convenient. So a chart maps into Rd, and of course on this level down in the chart we can check this function not only for continuity but also for differentiability. So here we have xi after x inverse, which is just the identity map on Rd, and of this identity map the ith component, which is of course differentiable. And when we are talking about a differentiable manifold, then the chart transition maps into different charts, let's call them Y, are differentiable, so this differentiability carries over to the differentiability in a different chart, and we can say that this function on the manifold level is continuous, because is differentiable, because this notion doesn't depend on the chosen chart anymore. So yes, we can tick this. The coordinate maps are oh no, I'm sorry. Question was whether they are not differentiable, and this is of course false. If Ux is a chart for a d-dimensional differentiable manifold, then these objects dx1 at the point P to dxd at the point P constitute a basis of Tp star m. Well, we can show that they do not constitute any basis, but a special basis, which is the dual basis for the coordinate basis on Tpm. And from there it follows that they constitute a basis of Tp star m. Let's show this. So, what is the condition for a dual basis? An element of this basis, dxi, the point P, acting on a basis vector del xj P shall be just delta I j. And this we can check via the very definition of the gradient. So this left-hand side is defined by the action of this vector on this function. So it is just del x j, point P, acting on the function xa. And this is also just a definition what is denoted here. It is the partial derivative with respect to the jth entry of this function in question, composed with the inverse of the chart map denoted down here, and evaluated at the chart image of the point P. And here in the brackets we just have the identity map on Rd, and of this map the ith component. And taking the partial derivative with respect to the jth entry of this map, here it's just delta ij, which is exact what we need in order for the condition for the dual basis to hold. So we checked that these elements constitute the dual basis of Tpm, so they constitute a basis of Tp star m. So this is true. For the basis del x1p to del xdp of Tpm, there's no dual basis in the dual space. This we just checked, so we can tick it. It is wrong, because we gave a dual basis, right? I'm sorry. The components of the vector x with respect to the chart-induced basis are dxi sub p x. Well, of course, this is true, because let's again write down what the components of a vector were. A vector arises as a velocity of a curve at a point P and was defined by the action of a function f via taking the function after the curve, thereof the derivative, evaluating at the point lambda naught, where lambda naught again was just the parameter value, where the curve takes the value p. So here we now can insert our chart map, the inverse of the chart map here, and here just the chart map, which just collapses to the identity, so we can do this. Take the derivative, evaluating, and now we may apply our multidimensional chain rule, because we can put brackets here and here. So what does the multidimensional chain rule do? We have to differentiate this inner function and of this inner function the ith component. Evaluate at lambda 0, and then comes the partial derivative with respect to the ith entry of the outer function. So di of the outer function f after x inverse, evaluating at x after gamma of lambda 0. So x of gamma of lambda 0. 1, 2, 1, 2, 3. Here you can recognize just the basis vectors with respect to the chart map x acting on the function f. So an abbreviation for this is del xa, the point p, acting on the function f. So these guys are the components of our vector. If we now apply this covector on this vector written here, we can extract just these components. Let me show it to you. Just have to apply this gradient del dx j, the point p, to our vector v gamma p, and via definition of the gradient we get the vector v gamma p acting on the function xj, and we know what this vector is doing. We calculated it here. We just have to put xj at the place of f, and this we already calculated up here, or along this calculation we would just yield delta ij if we put xj here. So we get this prefactor, the components, times delta ji, and of course this extracts the jth component of the vector. So this statement certainly is true. The expression dxa sub p acting on the basis vector del xa sub p yields the dimension of the manifold. Well, how could the dimension of the manifold come into play here? Well, let's take a look at this. We have this covector dxa acting on this vector And we already calculated this up here, right? And we just got delta ij. Now I and j are both a, so we write delta a. And now we have to remember our summation convention. Here we have an invisible sum sign with a running from 1 to the dimension of the manifold, which was d, summing over all these numbers delta aa, which are just 1 by definition. So we have the sum from 1 to d over the 1, and this is d, the dimension of a manifold. So this statement is true. Exercise 2. Virtuoso use of the symbol del over del xi sub p. This exercise is about getting familiar with this notion and a few other notions we introduced. Question. For a smooth function f and a chart ux, provide the definition of the expression del f over del xi p. This looks very much like the undergraduate analysis partial derivative. And to a certain extent it is exactly this. But here it is slightly different, because we have a function f mapping from the manifold M to the real numbers, function f, and this we can't differentiate, because M carries no differentiable structure. But we can use a chart map, which maps down into some RD, so that we can regard the function f after x inverse, mapping from RD to R. And here we can decide for differentiability and calculate these derivatives. And when it's about to calculate the ith partial derivative, well, of this function, we can take the partial derivative with respect to the ith entry, which then is just del I of the function down in the chart. And of course we can't put in the point P directly, we have to put it in down in the chart. So at the point x of P. This is the translation of the symbol above. Question. Show that for overlapping charts ux and y and vy, one has this relation. Here we will start with the right hand side, because we already know something about the right hand side. We did it in the first exercise. So delta AB can arise as the derivative in a chart X with respect to the eighth entry. No, A is below, so we have to write B here at a point P of the chart map XA. This will just evaluate to delta AB, which we showed in the previous exercise. We can evaluate the symbol. This is del B of XA after X inverse at the point X of P. And now we can insert here the identity written as y inverse after y, where y is our second chart map. So we may do this and then put brackets around these functions, xa after y inverse, and around y after x inverse. Yes. And evaluate at the point x of p. Now we may employ our multidimensional chain rule, which goes like this. Take this derivative of the inner function, or rather of the mth component of the inner function. So del b of the mth component of the inner function evaluated at the point, and multiply it and sum over m with the partial derivative with respect to the mth entry of the outer function, xa after y inverse, and evaluate at the point x of p, evaluated at y after x inverse. So here we really have to put y after x inverse of x of p. 1, 2, 3. Now, of course, x inverse cancels x, and we just can put y of p here in this bracket. And then we can translate these expressions back into our symbol. But now we don't have f, we have chart maps x and y. So this here reads down here xb, because we're using the chart x, and differentiate with respect to the bth entry. And which function do we differentiate? Well, it's ym. But hang on, m is written out here, not here directly at y. Well, this doesn't do any harm, because for the leftmost function it doesn't make any difference if we write m here or here, right? Because m indicates because this function takes values in Rd, and m just picks one of these values, and therefore it doesn't matter if you pick the value at the end, or if you say, well, just regard only the ymth component function, right? So we can write this here at the point P, and here it reads del of the function xa with respect to the chart map y, and here we have put the m at the point P, and this is what we had to show. We have to swap those expressions, but we can do this, and we got delta AB. Now, question. After inserting y inverse after y, the y is another chart map on the same chart domain U, at an appropriate position in the definition of the left-hand side, in this expression, we shall use the undergraduate multidimensional chain rule to show that it equals the right-hand side. Okay, let's do this. Therefore, we again have to translate this expression which we already did a few times. So this will just be del I of f of the x inverse at the point x of p. This is a translation of this. And now we can insert right here the identity map y inverse after y, because it takes values of the manifold and it again gives a value in the manifold. So this is the right spot for the identity on the manifold. Now we can again put brackets around the right functions, here around this function and here around this function. Employ the chain rule. So first del I of the inner function, and here of the mth component, times the derivative del m of the outer function at this point. Now this again yields just the identity map on the manifold, so we can just put y of p at the place of this expression, and then we can translate these expressions back to our symbols and we get del y m over del x I, the point P, times del f over del y m at the point P. So we showed that this left hand side really yields this right hand side. Question: do the dim m many quantities defined by the left hand side of the above expression constitute the components of a tensor? If so, what are the valence and the rank of the tensor? We will see that they in fact constitute the components of a tensor, and it will be a 0-1 tensor. So what do we have to check for this? Well, of course you can expand a covector omega if you have a chart map X into components with respect to this chart map, and of course the chart induced basis of the dual space dxi p. And you can employ a different chart y, and here it looks like this. Components with respect to the y chart times the chart induced basis elements with respect to the y chart. And in order for those two expansions to yield the same covector on the real world omega, you have to ensure that the relation between these components in the x chart and these components in the y chart fulfills a property, which you may call tensor component transformation property or something like this. And you can calculate it to be this condition: omega in the x chart, so the ith component in the x chart, has to be a linear combination of the components in the Y chart. In which combination? Well, it's given by these numbers. Del Yj over del Xi at the point P. And now we can compare with what we calculated above. If these are components in the X chart and these are components in the Y chart, the linear combination has to be with respect to these objects. And really, here we have these exact objects. So the tensor components transformation law for a 0-1 tensor is fulfilled. So these del f over del xip really constitute components of a 0-1 tensor. So this is the valence 0-1 and the rank is 1 because it is the sum of the 0 and the 1. Exercise 3. Transformation of vector components. Understanding the vector component transformation law the pedestrian way. Here it is about calculating real components of real vectors. Therefore, we have given a manifold R2 equipped with standard topology and with an atlas consisting of two charts. First, the identity map on hole R2, given here, and second, the map Y on hole R2, given here. First question is about calculating these objects. This we can just do in a very straightforward way by remembering the definition of these objects, which was del J of x, y, I after y inverse at the point y of P. Now we see, in order to calculate those objects, we have to know what the inverse of the coordinate map y is. So let's calculate it. This will just be a system of equations where y1 of AB equals A and y2 of AB equals B plus A cube. This we can invert, and here we can use the first equation to write B plus A cube is just y1 cube, so y1 of AB cube. So we calculated the inverse map. Y inverse of two numbers UB will just be the first number again, and the second number minus the first number to the power of 3. So V minus U cube. Good. And we already know what x after y inverse does with two numbers, because x is just the identity map. So again we get u and v minus u cube. Now we can calculate these four objects separately. We can start with del x1 over del y1 p. This is del 1 of x1 after y inverse at the point y of p. So del 1 of x1 after y inverse means we have to differentiate this function, which just gives u, with respect to the first entry, here u, which yields 1 irrespective of this point. You get 1. Now, what about the second component? So again it's del 1, but now x2 after y inverse y of p. Now, if we want to put numbers into this, we have to specify our point P by two numbers. So we call P, let's say, A and B. So we evaluate at y of A and B, and y of A and B is written up here. It is A plus A and B plus A cube. Now, we have to differentiate the second component with respect to the first entry, and this yields minus 2 u squared. So minus 2, and here we don't call it u, we call it a. So minus 2 a squared. And now we may turn to the next two objects, del x1 over del y2 p. This is del 1 x1 after y inverse. No, here we have del 2 at y of p. So first component with respect to the second entry just yields 0. And the last object is del x2 over del y2, the point P. So del 2 x2 sec y inverse y of p. And what does this yield? Well, the second component with respect to the second entry yields a 1 again, irrespective of the point where we evaluate. So these are the the four objects here. Now, here's a text where the transformation of vector components is being recalled. So a vector was defined by its action on a smooth function, like this. And we already did it in the first exercise. You can extract components with respect to a basis by inserting the identity map here and applying the multidimensional chain rule, and you get these components here. And these components we want to calculate for this specific curve. So let's do it. We'll start with the components in the x map, gamma x, and here the first component at the parameter value lambda naught. This is by the definition of this abbreviation the coordinate map after the curve gamma of this, the first component, the derivative of this, and evaluating at parameter value lambda naught. Now, x is just the identity map, so x after gamma of a parameter lambda just gives lambda and minus lambda. So we have to differentiate the first component of this map, lambda, which of course gives a 1, irrespective of this parameter value, lambda naught. Now proceeding the same way for the second component, 2, we get this time a minus 1. Now turn to the y map. Gamma dot y1 lambda naught. Well, this just is the y map after gamma, first component, derivative, lambda naught. Now we need to compose this curve with the y map. So y after gamma of lambda is what we need. Now we have to insert the point lambda and minus lambda into the map y, which is noted here. So we get lambda and minus lambda plus lambda cube. Again, lambda minus lambda plus lambda cube. And now we have to take the derivative of the first component, again just 1. For the second component, we get, oh, here it should say gamma two. Now we have to differentiate this component, which gives minus 1 plus 3 times the argument squared. So minus 1 plus 3 times lambda naught squared. And we calculated all 4 components. Now to the last part of this exercise. With the result of the first question, how could you have obtained the components gamma dot x from the components gamma dot y? Well, this question, of course, is asking for the transformation behavior of vector components, which is quite easy to derive, because we have to recall how you can calculate vector components. This goes by this expression, x after gamma I differentiated and evaluated at the point lambda naught, and here we can just insert the identity map written as y inverse after y. So this is x after y inverse after y after gamma, ith component, derivative at lambda naught, and now we have to employ the chain rule. We can put brackets here, and get the derivative of the mth component of this here. So y of the gamma m prime of lambda naught times the mth, the partial derivative m of the outer function x after y inverse I, because here we can put the I here, I and evaluating at lambda naught inserted into the inner function. So at y after gamma at lambda naught. So here we see just the definition of these gamma y dot m, right? So the components of the velocity in the chart map y. And of course in the chart map x we get a linear combination of these components, and this linear combination is given by this expression here. And what is this expression? Well, this is just our symbol, and we can translate it into the symbol by del x I over del y m evaluated at this point, gamma of lambda naught, which is just our p, because this lambda naught we always define this way. So this is the transformation law for vector components, and this law we could have employed to calculate, for example, the components in the x map from the components in the y map. We didn't have to calculate these explicitly. So how can we do this? So now let's check that we actually were able to do this. For the first component we get this linear combination gamma dot y1 times del x 1 over del y1 at p or let me denote the expression for p, gamma of lambda naught, plus the second component in the y map. Now here the 2 below, it's gamma of lambda naught. These objects we calculated in the first question and these in the second question. So we can read them off. This is 1 for the first component and minus 1 plus 3 lambda naught squared for the second component. So here a 1 and here a minus 1 plus 3 lambda naught squared for the second component. Now we have to read off these objects from the first exercise. Here we got a 1 for the second derivative, for the first derivative, and a 0 for the second one. So 1 and here 0, and in total we get 1, which we can compare with our previous result, where we also got a 1. Now we can do this for the second component as well. Gamma 2x, the point lambda naught, equals gamma dot y1 times del x2 now over del y1 at the point gamma of lambda naught plus gamma dot y2 times del x2 over del y2 at gamma of lambda naught. Now we can read off again. For the components, again we have 1 and minus 1 plus 3 lambda naught squared. So this, and we have to read off these two objects from above. There we got minus 2a squared, but for a we have to insert the first component of the point P equals gamma of lambda naught. So minus 2, and the first component in the y map can be seen here is just lambda naught. So minus 2 lambda naught squared. And I see I made a mistake in the previous exercise. Here, of course, when we differentiate a cube, we should have got minus 3a squared. And here it should also read minus 3. And the second object just gives a 1. So here we get a 1. Now we can put this together and see that these expressions cancel. This is minus 3 lambda naught squared plus minus 1 plus 3 lambda naught squared, and we just get minus 1, which now is the right answer. Here. Exercise 4, the gradient. Here you will see a special property of the covector named gradient you introduced. First we have to start with a notion of level sets. So, given a function f on a manifold M, let me draw a picture. So this shall be a manifold M, and the function f shall map to the reals, and we can draw the level sets of this function, so the sets where the function takes same values, which could maybe look like this. Here it takes value C1, here C2, and here C3. And these sets are defined like this. A level set for a constant C is defined by all the points P in the manifold at which the function takes this value C, like I drew it here. Now the question is to formulate the condition for a curve gamma to take values solely in one of the level sets of a function f. So we want to formalize this intuition that a curve gamma only remains For example, in this first level set C, goes maybe like this. Well, what does this curve gamma have to fulfill? Of course, if we look at the point at any parameter lambda, the point of the curve, the function f should yield the specific constant c. So we shall have this in order for gamma to lie in the level set of the function f with respect to the constant c, right? This has to hold for all lambda in R. So we can say the composition of the function f and the curve gamma has to be identical to the constant function c. At any parameter time lambda, we shall get, when we compose f with the curve, the constant c, right? Now, we have to show that if we take the gradient of this function and if we let it act on the velocity vector v of this curve, then we shall get 0, like it is written here. So let's calculate this. We take the gradient of the function f, the point P in the level set, let it act on a velocity vector to a curve gamma through this point P. Now, by definition of the gradient, this is this vector applied to this function. So v gamma p applied to the function f. And now by definition of the velocity, this is the composition of f and the curve. Of this composition, the derivative at parameter value lambda naught. And again, lambda naught is the parameter where the curve takes the value p. And now we have to use the condition to the curve gamma, namely that gamma is a curve which lies solely in a level set. And we saw for such curves gamma, this composition always yields a constant function. So here we're taking the derivative of a constant function, which gives 0. So really, the gradient of a function annihilates the vectors to curves which remain entirely in the level set of this function. Exercise 5. Is there a well-defined sum of curves? In the lectures, you defined the sum of curves with respect to a specific chart in order to define the sum of tangent vectors to these curves. And here it is about this construction and to see whether this is useful to really define a sum of curves and not only of the vectors. But let's go at this step by step. First we consider again the topological manifold R2 with the standard topology and equip it with this specific atlas. First mapping R2 with the identity map and mapping R2 with this map Y to R2. First question is whether A is a C-infinity atlas. Well, for a C-infinity atlas we have to check whether the chart transition maps from X to Y and from Y to X are C-infinity. So therefore we need first the inverse maps, which is quite easy for X inverse, for X, because it is just the identity so the inverse is also the identity and maps AB to AB. For y, we have to solve a system of equations. We set y1 of AB to A, like prescribed here, y2 of AB to B times e to the A, and have to solve this for A and B. The first one we can already solve. A is y1 of AB. And here we can insert the first equation and get B times e to the y1 of AB. Divide through this and get B. So B is y2 of AB over e to the y1 of AB, right? So y inverse just maps A and B to the second over e to the first. So, well, first to the first, A, and then what I said, the second over e to the first. So B is the second, and e to the first is e to the A. And now we have to check two functions for the C infinity property. First, let's take x inverse after y, which just maps AB to this expression, because x inverse doesn't do anything further with it. So we get A and B times e to the A. Well, is this C infinity? Of course it is. The first component is just mapping AB to A, which is of course C infinity, and the second component as well. Here we have the product of two C infinity functions, which is again C infinity. So this is C infinity of M. Right. Not of M, but of R2. To R2. So, a second charge transition map would be y inverse after x, mapping AB first again to AB and then to A and B over e to the A. So A and B over e to the A, which is again C infinity R2, because here we have a smooth function which we can readily see. Here we have the quotient of two smooth functions, and importantly, in the nominator we have a function which is only positive. So it is never zero, and now we know that the composition is C infinity. If it was zero at some point, this would fail, but here it doesn't. Now, second question. On M, we now consider two curves, gamma and delta. Gamma mapping lambda to lambda and 1, and delta mapping lambda to 1 and lambda. Now the question is, without referring to any chart, can we give the sum gamma plus delta of these curves? And the answer, of course, is no. Our topological manifold, or our manifold, is R2. And one might think, well, it's R2, so we can just add 2 bits of numbers. But this isn't true. Our manifold is just the space of all our positions. And not a vector space at all. So, and without vector space structure we can't add points, and without vector space structure we can't add curves. Vector spaces are our chart domains, our chart images. So this are two and this are two. They carry a vector space structure, but here we are asking if we could add two curves without referring to any chart. So again, no, we can't. Now we may try to give the sum of those curves with respect to a certain chart, and this is asked here, where we first shall calculate the representatives of the curves in the charts, illustrate them, and look where they intersect. So, step by step. The representative of the curve gamma in the x chart is of course given by this, and it takes lambda and gives lambda 1 composed with the identity map, so again lambda 1. Now for the second curve we get 1 lambda. So this we may also do for the chart map y, where we put in lambda, get lambda 1 first, and this we have to put into the chart map y, so we get lambda 1 times e to the lambda. So lambda and e to the lambda. For the second curve we get first 1 and lambda, and with the chart map we get 1 and lambda times e to the 1. So 1 and lambda times e to the 1. And this curves we may illustrate. So here in the x chart where this is our R2, here we have x1, here we have x2. The curve gamma is just a horizontal line with height 1. Imagine this being horizontal, and the curve delta, well, let me draw it more straightly. And the curve delta is just a vertical line intersecting the one at the x1 axis. So this is the curve delta. And of course they intersect here at, so I should specify this is actually x after gamma, and this is x after delta, so they are the images in the chart of the curves. And they intersect here in the point 1, 1 at the parameter value lambda naught equals 1. So this is the parameter value where this curve, the first curve, yields the intersection point. And lambda 1 is the parameter value for the second curve, but it also is 1. Right? At 1 both curves intersect each other. Now in the second chart, here we have again R2, Y1, Y2, and the first curve is the graph of the function e to the lambda, right? The y1 coordinate is lambda and the y2 is e to the lambda. So we get something like this, intersecting e here. No, intersecting 1 here, actually. And the second curve remains constant with respect to the first component. And so here, so is the horizon as a vertical line here. So what about the intersection point? Well, we see for lambda equals 1, we have 1 and e, and here for lambda equals 1, we also have 1 and e. So they intersect at the intersection point 1e, where the first curve has to take the parameter value 1 and the second curve as well. So let me draw the names again. This is y after gamma, this is y after delta. So you see, of course, with respect to different chart maps, curves may look quite different. Here especially this curve. The curve gamma. Now you may give the sum of both curves in this chart, which is asked in the next exercise, or in the next question. Now it's about to recall this procedure from the lecture, where you added those two curves and then subtracted 1 times this intersection point in order that the intersection curve, which may look like this, again passes this point. And then you could lift this curve again to the manifold by using this chart map x to the inverse. Then you get a curve in the real world. So let's do this for those two curves, this procedure. We want to give the sum of two curves in the real world. First with respect to the x chart. So curve sigma x of lambda shall live in the real world. So we take x inverse after our construction on the chart level. X inverse of the sum of both curves, lambda plus lambda naught, lambda plus lambda 1. So this is the sum of both curves in the chart, and we subtract the intersection point. Like this. This we calculated. So here we have to put lambda plus 1, because lambda naught and lambda 1 were both 1. Now we can plug these values into our curves. Here we get lambda plus 1 and 1 minus 1 and lambda plus 1 minus the intersection point, which was just 1 and 1. And actually we wanted to give the sum of two curves, not the difference. I'm sorry. Here. So this evaluates to x inverse of lambda plus 1 minus 1. So lambda plus 1 and 1 plus lambda plus 1 minus 1, so again lambda plus 1. And x inverse was the identity map, so we really get just lambda plus 1 and lambda plus 1. Right? The same we can do for the y map. Now with y inverse, y after gamma at lambda plus lambda naught plus y after delta at lambda plus lambda naught minus y after gamma at lambda naught. Putting everything in, we get first lambda plus lambda naught and e to the lambda plus lambda naught. So lambda naught was 1, so lambda plus 1 and e to the lambda plus 1, which is just e times e to the lambda. Then we get a 1 and lambda plus 1, because we're putting in lambda plus 1, and e. So e plus e lambda. Minus the intersection point, which was 1 and e. So we have y inverse of lambda plus 1 minus 1, so again lambda plus 1, and here e times e to the lambda plus e minus e plus e lambda, so e times e to the lambda plus e times lambda. Now we have to use the inverse of y, which we calculated up here. The first entry is kept, and then we have the quotient of the second and e to the first. So the first entry is kept, and the quotient of the second, e times e to the lambda plus e lambda over e to the lambda plus 1. I will use this space to draw the result, to give the result. This is lambda plus 1, and well, this cancels to 1, and this cancels to lambda times e to the minus lambda. So 1 plus lambda times e to the minus lambda would be the sum with respect to the y chart of the two curves. So this with respect to the x chart and this with respect to the y chart. Actually, this question was about this calculation for the y chart. I just did them both here. Now we can draw those two curves in the real world. R2 and R2, of course, you can draw like this because it is just 2 bits. Now, curve sigma x is this straight line through the point 1, 1 and 0, 0, for example. 1 and 0, 0. Goes maybe like this. And this curve sigma y is a little bit more complicated. So we are back with a plot of the second curve, sigma y of lambda, which looks somehow like this in the real world, and where they are intersecting in the point 1, 1. And we easily see, we already saw it with these expressions for the curves, that they do not coincide. So we saw this concept of adding curves down in the chart and then lifting the sum up is not invariant under the choice of chart, so it is really not useful. Now we saw that this addition doesn't make any sense. But what about the velocities with respect to these curves at the intersection point? This is what this question is about. We shall compare those two velocities, and we will do so with the components of the velocities. We already saw how to do this expansion into components. The components of the first velocity we denote by the curve, dot. We have to specify the chart, and we look at the first component. So, and of course at the intersection point of both curves, which is 0. Because at 0 we get for sigma x 1 and 1, and for sigma y 1 and also 1. So they were defined by taking the first component in this example of the composition of chart map and curve, but the curve isn't gamma here. It is sigma x, first component, they of the derivative, valuating at the point 0. And of course, we just get a 1, because this is x composed with sigma x, because x is just the identity map, and the derivative gives 1. The same for the second component. Second component again gives 1 here. Now these are the components of the curve sigma x with respect to the x chart. Now turn to the y chart, or to the, actually we consider the second curve which we constructed using the y chart, but in order to compare vector components we have to use the same chart here, so we will calculate the components with respect to the x chart again. Again the definition. Now sigma y, first component derivative at 0, will again just yield 1, because this is the first component of the curve sigma y. 1, and now the second component, is also defined like this. And this gives 0. Here we have a product rule, so we get 1 times e to the minus lambda. At 0 this gives 1. And then we get lambda times minus e to the minus lambda. If we insert 0, this gets 0. So 1 plus 0 is again 1. And we see the components of both curves with respect to the same chart x are the same. And therefore the corresponding vectors are the same, because the components give the whole expansion of the vector. For example, v sigma x at the point P. P is just 1, 1, the intersection point, was just these components. And the basis vectors. And the second expansion, of course, looks I'm sorry. And we just checked that these objects are the same as these. So the whole linear combination stays the same, and those two velocities coincide.